Hi there everyone, and welcome to the video on 8.2 integration by parts. We have one objective in this one, and it is to find an antiderivative using integration by parts. Please keep in mind this is the second to last video for the course this year. So I'll try to make this one semi-quick. So let's take a look at the integration by parts. Integration by parts itself is really based on the product rule. In the product rule, we saw that the derivative with respect to x of u times v was u times the derivative of v plus v times the derivative of u. Or we could think of that as uv prime plus vu prime. Now, that's a little bit different, opposite of what our chant said, but it still gets to this point, and it's really just how it sets up. So if I was to go and integrate both sides, so if I take the integral of the derivative of uv equal the integral of uv prime dx and plus the integral of vu prime dx. Now, keeping in mind that this portion here is equal to dv, and this portion here would be equal to du. Well, remembering how the antiderivative and the derivative, these two undo each other, the result of this is it's going to be u times v equals the integral of u dv plus the integral of v du. And really what happens, just doing some simple algebra now, and actually more just addition and subtraction, I can get that the integral of u dv is equal to uv minus the integral of v du. And that right here is what's called integration by parts. Theorem that we have for integration by parts: if u and v are functions of x and have continuous derivatives, then the integral of u dv equals uv minus the integral of v du. Now, really what happens at this point is this is actually a form of what the solution is going to take. And so really the key on this is going to be identifying what is u and what is dv. And then once we know what u is, then we can find du. And once we know what dv is, we can find v. And then we're able to plug everything in here. The other thing that happens on this, notice that I have an integral equal to this minus another integral, which tells us that there's going to be a second step once we do this. Either we're going to be doing integration by parts again, or this result here will be something that I will be able to take the integral of. We have a couple basic guidelines that we can go through in terms of trying to set this up correctly. The first one that we have, and they talk about in the book, is we're going to let dv be the most complicated portion of the integrand that fits a basic integration rule. Okay, so we're going to look at that integrand, and we're going to take as much as we can, and we'll let that be dv. But it must fit a basic integration rule. We can't just kind of pull it all over there, and if it doesn't fit, just say, oops, try something else. We got to go through and make sure it's fitting that basic integration rule. Okay, then u is going to be all the remaining factors of the integrand. The other thing that we do is we're going to try letting u be the portion of the integrand whose derivative is a function simpler than u. Okay, so it's going to be a little bit simpler. So that would mean things like if I have a polynomial, when I take the derivative of a polynomial, the degrees drop down, so it's a simpler function. Okay. So it's those types of things that we're going to be looking at. And then dv is going to be the remaining factors of the integral. Now, one of the things that we have, and you'll see it in the book, and I've seen it a couple other places when I was doing this stuff, is really, it really is the key is what am I going to pick for u? That's the way I've always worked with it. And so one of the things that they have in this book is an acronym to help us out. And that acronym is what you see right here, LIATE. And what that stands for. The L stands for logs. The I stands for inverses. A is algebraic. T is trig. and e is exponential. Those are what we have in terms of our choices. And so the idea is that when you're trying to make a choice on what you're going to pick for you start from the top, work your way down. So if I look at a problem and I have a log in there, that's going to be my first choice to let u be, because I know the derivative of natural log is 1 over x. If I don't see a log, but I see some sort of inverse, like an inverse sine, inverse cosine, things like that, that's what I'm going to choose. Algebraic would be the next one. That is those are polynomials, anything with x's where you have maybe x's raised to a power. And then the trig and exponential are pretty self-explanatory. Let's take a look at a problem involving integration by parts as an example. We've got a couple examples coming up here. The first one we're going to do is look at the integral of x cubed ln x dx. Okay. Now we go through on this one and really remember the integration by parts formula is that the integral of u dv equals u times v minus the integral of v du. So what I really have to do is identify what's u and what is dv. So in this case, remembering the acronym that we had before, the first choice for u is going to be a log. So in this case, I'm going to let u equal the natural log of x. And then dv, and I tend to put it right here, dv is going to be the remaining factors, so x cubed dx. So that means once I have that, now I can find du. Du is just the derivative of that, which is going to be 1 over x dx. And v is going to be the antiderivative of that, which is going to be 1/4 x to the 4th there. And so now I can go ahead and use the integration by parts formula. And the integration by parts formula again says that the integral of u dv is u times v minus the integral of v du. And so the integral of x cubed ln x dx is going to be u times v, which in this case u is natural log of x, v is 1/4 x to the 4th, so it's going to equal 1/4 x to the 4th times the natural log of x minus the integral of v du. V, in this case, v is 1/4 x to the 4th times 1 over x dx. And so if I simplify that, I get 1/4 x to the 4th ln x minus, now I'm going to pull the 1/4 out and simplify what I have there, so it's going to be 1/4 times the integral of x cubed dx. Notice the x to the 4th times 1 over x would be x cubed. And now what I have here is something that I can take the integral of. I know the integral of x cubed, it's 1/4 x to the 4th. So this problem becomes 1/4 x to the 4th ln x minus 1/4 times 1/4 x to the 4th plus c, or 1/4 x to the 4th ln x minus 1 over 16 x to the 4th plus c. There's the antiderivative of x cubed ln x dx. Now at this point, please pause the video to make sure that you are comfortable with everything that I did in this problem. And once you're done, if there are any questions, make sure to note those, and then we will move on to our next example. In our next example, we're going to look at x squared cosine x dx. Well, in this case here, again, remembering our rules for choosing u, I know that in this case, I don't see a log, I don't see an inverse, but now we're at an algebraic. Algebraic would be things, powers on x. So in this case, I'm going to let u equal x squared. And that means dv is going to be cosine x dx. And so, identifying at that point, we know that du is going to be 2x dx, and v is the antiderivative of cosine, which will be sine x there. And so with that, I can now say that the integral, using integration by parts, of x squared cosine x dx is going to equal u times v, so x squared sine x, minus the integral that I have of v du, which is going to be 2x sine x dx. Now at this point you look at that one and say, wait a second, this is not something I'm able to integrate. Well, what I do at this point is I now apply integration by parts again. Now the first thing I'm going to do is I am going to pull that 2 out of there. So this is going to equal, x squared sine x minus 2 times the integral of x sine x dx. And so we'll use those same ideas that we saw before. In this case, I'm going to let u equal x and dv equals sine x dx. And so du is going to be 1 dx, or just dx, and v is going to be the antiderivative of sine x, which is going to be negative cosine x. And so now what I get, applying integration by parts again, this thing is going to come out to equal x squared sine x minus 2 times u times v, which is going to be negative x cosine x, minus the integral of v du, so a negative cosine x dx. Simplifying that a little bit further, that's going to equal x squared sine x plus 2x cosine x minus 2 times the integral of cosine x dx. And again, we know the integral of cosine x is sine x at this point, so we're able to finish that one off. And so I get this is equal to x squared sine x plus 2x cosine x minus 2 sine x plus c. And so I know now that the integral of x squared cosine x dx is equal to this. That's the antiderivative. Again, at this point, please pause the video. Make sure that you're comfortable with everything I did on this one. And if there are any questions, please write those down, and then I'll proceed to the third example. In our next example, what we have is the integral of e to the 2x sine x dx. Now, the interesting thing about this one is, remember how one of our guidelines, in this case for choosing u, was that we wanted this thing to be u to be something that would become simpler as we took the derivatives. Well, in this case, because of what we're dealing with here, e to the 2x, when you take its derivative, doesn't become simpler. And same with sine x. It doesn't become simpler. It stays, the derivatives of sine are going to become cosine. Derivative of cosine will become the negative sine. But we get, it's just going between those two. And the derivative of e to the 2x is going to be 2e to the 2x and then 4e to the 2x. And so you see it's not getting, neither one is getting simpler. That's why, though, that's where one of the unique things about this type of problem is the fact that really neither of them are actually going to disappear. So it's going to look a little bit strange as we go through this. But remember, our guidelines is to let u be, would be the, when we get down to far enough, we get to the trig. So trig, and then the next one down would be the exponential. Quite honestly, I've seen people do both here. I've had some people let u equal the exponential and then dv equal the trig function. So it really doesn't make a difference. In this case, though, I will follow the acronym. And what I know in this case is that I'm going to let u equal sine x and dv equals e to the 2x. And so when I do that, du is going to be the derivative of sine x, which is cosine x, dx. And, I should put the dx with the dv. And v is going to be a function whose derivative will be e to the 2x. So it's going to be 1/2 e to the 2x. And so what I get when I do that, when I put that in, I'll get that the integral of e to the 2x sine x dx is equal to u times v, so 1/2 e to the 2x sine x minus the integral of v du, which is going to be 1/2 e to the 2x cosine x dx. And again, at this point, I can pull that 1/2 out, and so I'll deal with that when I rewrite it. But the next thing I have to do is integration by parts again. And so at this point here, I'm going to go through and I will follow that same process. In this case, u is going to be cosine x. And dv is going to be e to the 2x again. And so du is going to be negative sine x dx. And v is going to be 1/2 e to the 2x again. And so when I set this up, I'm going to have now that the integral of e to the 2x sine x dx equals 1/2 e to the 2x sine x minus, now that I'm going to remember I talked about pulling that 1/2 out, so minus 1/2 times the integral of, or times the integral of the e to the 2x cosine x dx, which I know by integration by parts is again going to be u times v, so it's going to be 1/2 e to the 2x cosine x minus v du, which is going to come out to be 1/2 times the integral of e to the 2x times, well, it's a negative sine x, so that's going to make that a plus 1/2 e to the 2x sine x dx. Which this problem becomes now the integral of e to the 2x sine x dx equals 1/2 e to the 2x sine x minus 1/4 e to the 2x cosine x minus 1/4 times the integral of e to the 2x sine x dx. Now at this point you're saying, wait a second, this is just going, you should be thinking this is just going to continue cycling through here. Well, there's one other thing that we have though. Please notice what's on the left hand side. It is the integral of e to the 2x sine x dx. And I'm taking, and over here I have minus 1/4 e to the 2x sine x dx. In essence, these two here are like terms. And so I can add this term to both sides. And when I do that, because this is 1, and I'm going to add the 1/4, what I'm going to get is 5/4 times the integral of e to the 2x sine x dx equals 1/2 e to the 2x sine x minus 1/4 e to the 2x cosine x. We can go with the plus c at this point too as well. And what I can do now is just, remember what I want to do is I want to just find out what this integral would be. I don't care, I don't want what 5/4 of that's going to be, so I'm going to multiply both sides by 4/5. And when I do that, I'll get that the integral of e to the 2x sine x dx equals, multiplying through by 4/5, that is going to be 2/5 e to the 2x sine x minus 1/5 e to the 2x cosine x plus c. And that would be my final answer for this particular integral. Now with that, there is one other method I will show you in class. It's called the tabular method. It really gives, it's a way to do problems similar to the second example I just did. Especially, it's especially helpful when there is more, when it's going to take more than just using integration by parts 2 times. So that will be, we'll look at that in class, but this now does conclude the video on integration by parts. If you do, again, if you do have any questions, make sure you ask them. And with that, I will see you in our next class.